So this is the next video in this series, and this lecture is about the Cartesian coordinate to cylindrical coordinate transform. And again, it's possible to transfer from cylindrical coordinates to Cartesian coordinate. So these are the two coordinate system in which you want to transform. So again, this is part of the vector algebra and I'm detailing it. So if you have a simple coordinate system like x, y and z, this is a Cartesian coordinate system, and if you are moving in the clockwise direction, then this is a right hand Cartesian coordinate system. So, and it's possible to write a vector a in the Cartesian coordinate system as ax into ax plus ay into ay plus az into az. So I have made some videos about this, so if you want to go into detail you can go into detail, but this is known as the component in the x direction, and this together, both of this is known as the component vector in x direction. So ax into ax is a component vector, and this is the magnitude of the component vector in the x direction. So again, this Cartesian coordinate system is made up of three planes, so it is possible to represent any point in space using x, y and z, and x, y and z are three planes. Like the x is going from minus infinity to infinity, and y is going from minus infinity to infinity, and z is going from minus infinity to infinity. And the next kind of coordinate system which we are going to deal with is the cylindrical coordinate system. And in the cylindrical coordinate system, so if taking a simple example, it's possible to represent a point in space using three things. The first thing is a plane with an angle phi. So if I'm having this is my x, this is my y, and this is my z. So if I'm having a phi angle with making with the x axis, and I'm extending this, then this is a plane with the angle phi. And the next is the plane of z axis. So and the next is what is known as a cylinder of radius rho. So this is my rho radius and this is my cylinder. So from here, whatever is there, I will form a cylinder. So this is my cylinder, so it's extending, and this cylinder will cut the point P at what is known as a z axis. So based on my phi, based on my rho, and based on my z, it's possible to locate a point. This is my z, this is my what is my rho, and this was my phi. So it's possible to locate a point, and in this case your 0 will be always less than, or you can represent the three things as your cylinder will be going from, it will extend from 0 to rho to what is known as infinity. Writing it here, it will be 0 to rho to infinity, and your plane will be from 0 to phi to 2 pi, and what is your z will be from minus infinity to z to infinity. So this is how you can represent 3 points, and this was a basic overview which I want to give for, and this again I have prepared a video so you can go through that video to get in detail. But what I want to say is that it's possible to represent a vector like ax into ax plus this is a vector, and ay into ay plus az into az. So this is a vector in Cartesian system or Cartesian representation, and this is a vector. It is possible to represent it in a row plus a phi plus az, and this is a vector representation in cylindrical coordinate system. So these are the two ways to represent the same vector in two different coordinate system. So when you're dealing with the Cartesian coordinate system, when you're dealing with a cylindrical coordinate system, the Cartesian coordinate system will have three unit vectors. This is a unit vector in x direction is a ax, the unit vector in z direction is a az, and the unit vector in y direction is a ay. And you are going through the right hand, and when you are dealing with the same point in the cylindrical coordinate system, your phi will be somewhere, this will be a row, and this will be how your phi will be varying. So this is your minus a phi, and this is your how your phi will be increasing. So this is your plus a phi, and again this is how your row will be increasing, or in this direction a row will be increasing, and this will be the direction of your z. So this will be perpendicular if you are seeing in 3 dimension, but it's not possible to show it in exactly 3 dimension here. So this is how your 3 unit vectors will be in your cylindrical spherical coordinate system, and these are the 3 unit vectors in Cartesian systems. So now the task is how you will be transferring from cylindrical Cartesian to Cartesian system to cylindrical and vice versa. So again, just erasing this. So simply what is possible is to find the relation. You'll have to draw that diagram again, and this is your z, this is your x, this is your y, and this was your row, this was your phi, and this was your z. So what you see is that this phi will, this row will make, this was your radius of your cylinder, this was angle phi which was a plane. So what you see is this will make a row sine theta here on the y axis, and it will make a row cos theta on your x axis. So it's possible to say that your x will be equal to the row cos theta, and your y will be equal to the row sine theta, and your z is equal to the z itself. And when you are taking the x square plus y square, which will be equal to the rho square into sine square theta plus cos square theta, which will be equal to 1. So your rho is equal to under root x square plus y square. And again, it's possible to find the angle phi is equal to tan inverse x by y by taking the ratio of these two. So that was how you were finding your phi, and your z was equal to the z itself. So in this way you found out the relation between the three components. So like how it's possible to transfer from one coordinate to the other if you know the components like rho, phi and z, and again if you know the x, y and z, it's possible to transfer from one coordinate system to the other coordinate system. So that's how you are doing the transformation. Again, it's possible to transfer from one coordinate to other. The next is how to convert each of these values in such a way that if you have values like it's possible to write based on if you have a row and a row vector, a phi vector, a z vector, and you have all these values and you want to now write this in form of this. So we will see how it's mathematically or it's possible to derive that. So considering redrawing from what we have drawn in a simpler way, I'll draw it here. This is my y-axis and this is my x-axis, considering only those two. And now I have what is known as my, so I'm not taking the case of z here because it's already the same thing. So this is my, what is my row, and if I take a simple area of this, if I say that this is my a row and taking this way, and this is my a row and this is making an angle phi, and this is my phi angle. So this is my phi in the increasing direction, this is my phi in the decreasing direction. So the next step is to find out the value of ax and ay in terms of a row, a phi and a z. So since the row, that is the radius, and phi is only the new components here, which is different from the cylindrical which is different from the Cartesian coordinate system. So the az will be equal to az in both the coordinate system because z is the same while we are considering for both the coordinate system. So it's possible to find out the value graphically of the ax in form of a row and a phi as this way. So while you are considering that this is the unit vector of the radius of your cylinder, that is a row. So this is my row and this is a row, and this is the and at 90 degrees to that, what you have is your, and this total distance is my ax, which I needs to find. So what you are doing is that you are taking the minus of a phi. So at 90 degree, if you go into this direction, this will be my, at 90 degree with the a row will be my a phi. So this will be my a phi, and the phi is increasing in this direction, it is decreasing in this direction. So when you are considering this is your minus a phi unit vector, and this is making angle phi with the y-axis, and when you are projecting it on this side, what you are getting is a phi cos theta, and when you are projecting it on this side, you are getting what is known as your a phi sin theta. And you are taking this as it is, since you are constructing a parallelogram. You are taking the a phi as it is, and you are projecting it here, and this is making angle phi here, and when you are projecting it on this side, it will make, the projection will make a rho cos phi, and this will be a rho sin phi. And you can, by vector addition, if you are putting it on top of here, on top of this vector, that is a rho sin phi plus a rho cos phi, what you will get is a vector ax. So in this way you have found the vector ax, and it is similarly you can find the vector ay. So continuing drawing the same graph in a different way, that the x and the y axis, you have the a rho which is coming, which is a unit vector for the radius of the cylinder. So you have this unit vector, and this is making angle phi with the x axis. So when you need to find out what is the ay. So this is your ay, that is the unit vector in the direction of the y axis. If it is in this direction, it is starting from here, it is in this direction. So this is the ay you need to find out. So this is your a rho unit vector, and 90 degrees to that is the unit vector of a phi and minus a phi. So this is making angle theta with the y axis, or the axis which you have considered here. So when you are projecting it on this side, what you will get is a phi cos phi. And if you are drawing the a rho here, if you are projecting the same thing here by vector addition, so you will, and if you are, this will be making angle phi with this axis, and when you are projecting it on the y side, what it will be getting, you will be getting a rho sin phi. So this whole distance which you can see is the summation of a rho sin phi and a phi cos phi, and in this way you are getting this, and already you have got this. So I'm just stopping here to, so I've just showed you how it is possible graphically to get the conversion. And if you are writing down what we have got so far, so conversion of Cartesian coordinate to spherical or to cylindrical spherical coordinate. So the first thing which we got so far is that it's possible to write the vector a is equal to ax plus ay plus ay plus az plus az. So az. So this is how we are writing in the Cartesian system, and to write it in the spherical system you have to take the respective coordinate components and the unit vector, that is a rho a phi plus az. This was in cylindrical system. So these are the two things which you got so far. And when you are getting the rho, which you got was x square plus y square, and the phi is equal to tan inverse of y by x, and the z will be as it is in z. So it is possible to convert the values from one coordinate system to the other. This is if you are using the graphical way. Graphically, if you are converting it, then you can do it based on the value of the x, y, z and the phi which you know. And again, x is equal to rho cos phi, and y is equal to rho sin phi, and z equal to z. So this is the second set of equations which we derived. And then what we derived was, we derived the value of the different components. So it was possible to find out AX So now what, based on what we have derived, what we found out was, for graphically it is possible to show that AX is equal to cos phi A rho minus sin phi A phi, and AY was equal to sin phi A rho plus cos phi A phi, and AZ equal to AZ. So this is what three equations which we found graphically, and again from these three equations it is possible to compute it in form of A rho is equal to cos phi AX plus sin phi AY, and A phi equal to minus sin phi AX plus cos phi AY, and AZ equal to AZ. So from based on this equation it's possible to again write. Now if you want to convert the first equation in form of second equation, this is the first set of equation which you got, this is the second set, and these are the third set of equation which you got, and these are the fourth set of equation we got. So if I am substituting the value in the first set of equation, what I will get, A is equal to AX into cos phi A rho minus sin phi A phi plus AY is equal to sin phi A rho plus cos phi A phi plus AZ equal to AZ. So based on this it's possible to write it as A is equal to So based on this it is possible to write A is equal to AX into cos phi plus AY into sin phi, and the whole thing you can take A rho common. So this is just solving this further, and minus AX sin phi plus AY cos phi into A phi. So this is a unit vectors plus AZ AZ. So that's how it's possible to convert from the Cartesian coordinates to the spherical coordinates, or to convert from the spherical coordinates to the Cartesian coordinate system. And this is equal to A rho, and this is equal to A phi, and this is equal to AZ as it is. So if you have some values which is given in form of AX and you have found out the phi, then it's easily possible to calculate the value of A rho and A phi, and you can easily convert this equation to this equation. So you have only AX, you don't have A rho, so you can find out A rho from this equation. And in similar way, if you are substituting this here in this equation, it's possible to find out the values in form of AX. So if you have it given, if you only have X, Y and Z, so it's possible to calculate rho, phi and Z. So it's possible to convert both of them either ways using this. So these are the basic equations of conversion and how you actually derive them.